Last week we had a quiz, so I'm going to go over that real quick. We have another quiz this week that's due on Friday, quiz 3. It only has 5 questions. So quiz 2 asked, consider the following system Verilog module. What is a problem with this module? So this actually has a typo in it. So when I wrote this question, I had intended to take the else part off of this. And the answer was supposed to be the always block has no default assignment for C, but actually it does because of that else, the else. So I gave everyone credit for this one. And I also tested it because I thought maybe the compiler or the model sim compiler may still complain about that. I mean, normally, I shouldn't say normally, but it is, in this class anyway, often we put default assignments before the if statement. So like you would assign C before that as a default, but as long as you have the else there, it's fine. Does that make sense for everyone? Right, it means that C will get assigned regardless of the outcome of the if. Okay, so that was a fail. Sorry about that. Question 2 said, consider the Verilog module shown below. How many input signals are specified? We've got clock, reset, load, and seed. Seed is 8 bits, but it's still a signal. So that was supposed to be 4, I believe. And then consider the system Verilog module. Assume the module is reset with a reset pulse at the start of execution. What's the value of the state in the first 3 cycles after the reset pulse? So the reset will set state to 100, and then after you deassert reset, the value of state will change every cycle. And so we're going to start out with 100, and then in the next cycle, in the next cycle, state 2 will become 0, state 1 will become the previous state 2. So this is the tricky part here is in order to figure out the previous state of state 2, you got to go up to the previous cycle. So state 2 would have been the first bit, the most significant bit, which is 1. So the new state 1 is going to be the old state 2. So state 1 will be 2, and then state 0 is the old state 1 or the old state 0, right? Which is going to be 0 or 0, which gives you 0. So the value in cycle 1 will be 0, 1, 0. And then in cycle 2, state 2 will still be set to 0. State 1 will be 0 because the old state 2 was 0. And state 0, the new state 0 will be, let's see, 1 or 1, right? The two low order bits of the previous state ORed, which is 1. So the value there is 0, 0, 1. So the sequence will be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, question 4, very similar, except this one actually mixes the blocking and non-blocking assignment statement, which you can do. It's not too common, I don't think, but same question. You have a reset where that'll reset A to be 101, and then in the next cycle you're going to shift A to the left by 1 bit, the old A, and so it'll go from 010 to 010, right? Because that first 1 will get shifted off, and so then you'll shift in a 0 on the right hand side, right? So so I'm showing it here. So you're going to take 101, shift it left 1 bit to get 010, and then you're going to XOR it with 111, which will flip all the bits. So it'll become 101. So the point of this question is that the shift happens together with the XOR because of that blocking assignment statement, right? So what this means is this is equivalent to, you could rewrite this where you shifted A and then did the XOR all in one line of code, right? One expression. But because of this blocking, you're going to honor the dependency here between these 2 lines of code. Again, meaning that you shift and then XOR it. And then once you get to cycle 2, you're going to take the old value of A from the previous cycle, which is 101. You're going to shift it to the left by 1 bit, which again makes it 010, and then you XOR it with 111 and you get 101. So in other words, this will always be 101, right? It'll just keep setting it to 101 over and over again. It'll never actually change the value of A. Any questions? Okay. What's the problem with this code? Okay, this has A being an input and an output, so this is creating a loop, a combinatorial loop. And so you can't do this in combinational logic. And so this will generate an error because the always explicitly has the underscore com, meaning that you're telling the compiler it should be combinational logic. So this is essentially sequential logic that is being defined in an always com, so you'll get an error. So yeah, so I think the answer is A, always statement should be combinational but has a cycle. Does that make sense? So it also has a missing sensitivity list, but that's okay because that's always comms don't have an explicit sensitivity list. Any signal that's treated like an input will be inferred or is automatically added to the sensitivity list. You guys with me? And then cannot use addition and always com statement. That's not true. You can do that. And then use a blocking assignment. That's fine too. In fact, that's the kind of the convention. If always com, you use the equal sign, a blocking assignment. Okay, then we have consider the following test bench. What function does some module perform? So in this case, you can see from the test bench what the inputs and the expected output is of some module. So some module is declared at the top with connections for A, B, and C. And you can't tell from the instantiation of some module which of these are input. You don't know if A, B, and C are inputs or outputs until you get to the code, which it's setting A and B and looking at C. So A and B must be the inputs and C must be the output just based on how it's coded. And then this is tough. I mean, really the only way you could do this is by putting the inputs and the expected output into a table and then looking at that table to try to figure out what that table looks like. And in this case, it's an AND gate because the output is going to be, the expected output is always 0, except for when A and B are both 1. Okay, so you can, in other words, you can tell what the thing is supposed to be doing from the test bench, which is possible just because it's, in this case, because it's so simple. And what are the 3 values of A generated in the snippet below? This one is a linear, is it? No, it's kind of like a linear feedback shift register, but not really. It's this one resets with 10101. Okay, 10101, and then as it evolves after the reset, you have to do some bit twiddling here based on the previous state of A. So let's see. So the curly braces are a concatenation operator, and they are ordered from most significant to least significant. So this first thing is going to be A4, right? The most significant bit of A. So the first bit is going to be the least significant bit. The most significant bit is going to be the previous least significant bit. So if you go, this 1 over here in A0 is going to transfer up to A1 in the next cycle. And then you have 2 copies of A bit 1, which is 0, so there's 2 zeros. And then you have the complemented A3, which is 0, is now 1. And then you have the XOR of the old A2 and A4. Let's see, A2 is 2 and A4 is, A2 is 1 and A4 is 1, and 1 XOR 1 is 0. Okay, and then you just do the same thing to get the next value, right? So the point of this is understanding that inside this clocked always, when you refer to A, you're referring to the previous cycle version of A, right? The previous, what A was in the prior cycle, right? Because of the clocking, right? Now remember, I had this thing here, this guy, right? This also did the same thing. This said A equals A plus 1, except this wasn't clocked. So this was not valid because this was an always comb. But if it were an always at pos edge clock, then it would be fine to, to have inputs, the same signal as an input and an output. Make sense? Okay, good. Okay, so in lab, I very quickly went through some material you needed for the next project. I want to review that a little bit just to make sure everyone's clear on that. So I talked about the three-stage pipeline. First stage we fetch. Second stage we decode and execute. Third stage we write back. The fetch stage is pretty trivial in this lab. It's just the program counter and the incrementer for it. The control unit is taking the control information from the instruction, which is the opcode and the two function fields in the CSR, and basically just translating those to control signals. And then the reg file is got connections for the RS1 and RS2 registers into the two read ports, and then the write address is taken from the RD field, but with a 1 cycle delay in order to get that piece of the instruction, just that piece, bits 11 down to 7, the RD field, gets delayed by 1 cycle before it gets put as the write address in the register file. So I talked about how it's, I mean, really this design is simple, but it can be tricky to debug. So we're always looking for ways to try to make it easier to debug. And so one of the ways to do that is to rename all, how many are there? 9? Yeah, there's 9 total fields across the 3 encoding formats. So we have R-type, U-type, and I-type instructions. And there are 9 fields, some of which are overlapping. So for example, the immediate 20 is used in the U-type instruction, but it actually uses 12 of the bits from immediate 20 are also included in immediate 12, right? Why? Because immediate 12, let's see, where's the here we go. Yeah, so you see immediate 12 and immediate 20 overlap. So the leftmost 12 bits of immediate 20 are immediate 12, right? Likewise, func3 is common in the R-type and the I-type, but func3 is part of the immediate 20 in the U-type instruction. So this renaming process, has some redundancy in it because these are not, some of these fields are overlapping. In the control unit, you can structure the if-then-else condition to first figure out what encoding format the instruction is, and you can tell that from the opcode, right? And then once you know that, then you can look at the other fields. Does that make sense? Okay, so this thing just renames the instructions. We call it decoder, and then that's separate from the control unit. And then the reg file we give you. And then the instruction memory is initialized through RARs. I think this is kind of neat how you can assemble your code in RARs and read it in directly into your design. So this code, you can use this code directly in your CPU. This is a good starting point just to set up the fetch stage. And then we've got the control signals reg write, reg select, and op, which are generated by the control unit and control whether you write to a register, what you want to write in the register, and what you want the ALU to do. The ALU code, the ALU table is, where do I have that? Somewhere here. But that op-ex is a 4-bit signal that goes in the ALU, and we just made that up. That's not part of the RISC-V spec. That's just an arbitrary table that we set up when we design the ALU. It tells the ALU to do what to do. The only way to use that is to look it up, right? So you know that you want to do an add or subtract, so you look up add or subtract, and you find the ALU opcode for that, and you would just put that into your control unit for that instruction. So reg write and reg select are often going to be the same value for all the instructions. So reg write is going to be 1 whenever you write a register, which is all the instructions are writing a register except for the one of them, the CSRRW instruction, one of the 2 variants of the CSRR instruction. Reg select is often going to be, most often going to be 2. So if you trace this wire over here, you can see 2 is routing the ALU result through this mux. So this mux is taking care of what you want to put onto the write data input into the register file. Okay. Now, in your code, you can actually combine these registers with the mux by essentially just creating a mux, but putting in a clocked always. Right? So if you create a mux, in other words, you create like a, use a ternary operator, or you use an if then else. All you have to do is put that in an always FF at pos edge clock, and you get the registers and the mux just together into one block if you want. So these registers are, clocked logic. Mux is combinational, but like I said, you can combine those. This bmux though is has to be purely combinational. There shouldn't be there should be no clock involved with this mux. Now there would be if we had split this into a 4-stage pipeline. A 4-stage pipeline would put a pipeline register between the register file and the ALU. In a good place to, probably you'd put that before the mux, I would imagine, right? You'd put a pipeline register there, and then you can create a 4-stage pipeline, which should let you run the clock faster, right? Having a 4-stage pipeline, but it complicates data hazards. If you have an instruction that writes a register and then the next instruction reads the result from that, you have to implement forwarding if you have that additional pipeline stage. So we don't have that. We did a 3-stage pipeline just to simplify that part of it. And then we have the only other block here. Oh, there's 2 other blocks you have to worry about. The sign extending, which is used for I-type instructions. You have to convert the 12-bit immediate to a 32-bit value using sign extension, and Verilog provides a very convenient way to do that through the bit duplication operator it has. And then there is this, and this is the ALU mux. I just already talked about that. Just shown from a different perspective. Okay, so the whole CPU design is shown here. I think I have all the pieces in here. It's a little tricky to read because you've got the I/O, this is the switch value, I call it I/O 0 in. This is the 32-bit switch value. Of course, there's 18 switches, so you have to pad it with zeros. But that comes in over here. And then there is a output to the hex displays over here called I/O2 out. The reason why we call it I/O 0 in and I/O2 out is just to give them generic names for the GPIO. Any questions about this? Is this clear? Now this version, by the way, does not have the decoder in it. This is the version that just takes the instruction fields and sends them directly into the control unit. So if you had the decoder that renames those signals, you would insert that right over here. I don't remember why that's not in this design, but it would just be a box that goes right here. Any questions? All right. Okay, so we went through some examples. So quiz 3 is just asking you, I think most of the questions on quiz 3 just ask you to fill in this table for a few different instructions. It's a little bit more complicated than that, though, because the way I'm showing the table here is This is just in the execute stage. So this slide is showing what the control unit generates in the execute stage. On the quiz, I also ask you some of the control signals. I ask you what they are in the write back stage, which would be whatever they were in this stage in the prior cycle. Okay. Okay, so in this case, we've got 4 R-type instructions, so ALU op would just have to be set according to what the instruction mnemonic says to do. So for subtract, you have to look up subtract in this table, and you can see the ALU op there is 0, 1, 0, 0, for instance. So the control unit would essentially be interpreting the opcode, the function code, and the 2 function codes to be an ALU op. Now, what are the... I've never looked at this very closely, but it looks like for example, add and subtract have the same opcode and the same function 3 code, and there's just a 1-bit difference in the function 7. So the function 7 appears to be a way to discriminate kind of closely related operations. So add and subtract are kind of close, so they just differ by 1 bit in function 7. Likewise, multiply 2 also has the same opcode in function 3 and just differs by a single bit in function 7. But set less than has a different function 3. So maybe function 3 being zeros means arithmetic, and function 3 being 0, 1, 0 means comparison. I don't know. I don't know exactly how they chose those encodings. But all of those encodings are in the lab sheet, and we have a PDF on Blackboard as well. And of course, if you look up anything about RISC-V, like if you find a reference card or an ISA online, we're consistent with that too. So you can use any RISC-V table of these codes to figure this stuff out. Okay, so ALU source is 0 for all these because they're all R-type, so we're not using the immediate. In fact, we're not using the immediate field. Reg select is always 2, which means use the ALU result to write back. Reg write is always 1, and GPIO write enable is always 0 for these because none of these are the CSRW instructions. Okay, this table shows 2 R-type and 2 I-type, and so again the ALU op will depend on what the operation is. Whether you do an AND or an AND-I, of course you'd use the same ALU op, which is 0, 0, 0, 0 for AND, and then shift left logical would be the same. Shift left logical immediate would have the same opcode as well, 1, 0, 0, 0, which is over here. So that's a shift left logical. That's A less than B. So I'm using the Java/C operator for that. ALU source will depend on whether it's R-type or I-type. So if R-type it's 0, I-type it's 1. So we have 2 zeros and 2 1s there. Reg select is going to be the same for all these because they're all writing back the ALU output. So 2. Reg write is going to be 1 for all of these because they all write back. And GPIO write enable will be 0 for all of these because we're not doing any I/O. And then finally we have these 3 oddball ones, load up or immediate. We don't actually care what the ALU op is, actually for any of these. So load up or immediate and the I/O op instructions don't use the ALU op, or they don't use the ALU, so the ALU op is a don't care. ALU source is also don't care. Reg select is a 1 for the LUI. So the trick here is you have to follow the line for, let's see, for LUI, you need to follow this guy, the immediate 20. So how would you know this? You have to understand what the LUI does. The LUI loads loads an immediate into the upper part of a register, but it's also unique in RISC-V in that it has a 20-bit immediate, unlike MIPS that always used a 16-bit immediate. Make sense? So load upper immediate is the only U-type instruction, so you have to find the immediate 20 field for that. So the immediate 20 is over here up in the upper left-hand corner, and if you trace the wire, it routes through, well, it first goes through a register, but then it routes through input 1 on this mux here, so the reg select mux. So that mux select for that should be a 1. And then for the switch, if you want to write the switches, we want to use GPIO in. And by the way, okay, so this is a little sloppy. So I call it GPIO in. Previously, I had shown it as IO0 in. So the naming is a little inconsistent. The point is that this is the input from the switches. You're routing it through this MUX through input 0. So the reg select should be 0. So I apologize for that. I should have called this IO0 in. Likewise, the one over here should be IO0 out. Or sorry, IO2 out. And then reg write is a 1 for the LUI because you're writing a register, and it's a 1 for the loading the switches because when you read the switches from the DE2 board, it's going into a register, so you have to write it. Whereas for the hex display, that's strictly an output, and so I would set the reg write to 0 there. Now this is a little weird though. This is non-standard because as I mentioned in the real RISC-V processor, actually all the CSR-RWs would write a register because they do like a swap. They take the control register, they put it in the register file, and whatever's in the register file gets put in the CSR control status register, right? So this is non-standard for us. This is something, setting this reg write to 0 for one of the CSR-RWs is not fully compliant with RISC-V. I don't think it really matters much though, because if you use the CSR-RW instruction and you want to write to the hexes, you can specify register 0 as the destination register, in which case it doesn't matter if you write the register or not, right? So it's not really important. This is not really critical that you set reg write to 0 for this, as long as your code always puts a register 0 whenever you want to write to the hex displays. Then it's not a problem, right? Then who cares? Write to a register or don't. So I don't really, in other words, it doesn't really matter. And actually, if you do allow this guy to write a register, then pretty much all your instructions are going to write a register, which kind of makes the whole reg write signal redundant in this lab, right? You could just hardwire it to 1 for this lab if you decide to write for that hex instruction. Now in the next lab, that won't be true, right? It's only for this one. And then finally, GPIO write enable. This, as I mentioned, this is an important one. This is the most common bug that students have in this lab is that they hardwire this GPIO enable to 1. And so they get the right result, but then it gets cleared. You know, they lose it. They don't have any way to lock in the hex output value. So make sure you have a way to lock that in. So what this is an enable signal that allows you to capture a value in the output GPIO, you know, the hex display, and keep it there until the next go round of your program when you recalculate it. Okay, so here's the whole table, everything put together. This is about half the instructions, so this is essentially half of the lab. But you know, you have to translate this into system Verilog. That's the challenge. Okay, then we have a test program. So this is a little bit vague in the lab. So hopefully I can clarify this. So the test program, we want you to use this test program. We want you to be able to run this test program and verify that it works. But we also want you to have some test bench. We're always vague about how you implement the test bench. It's however you want to do it. This is a part of the class that we're hoping that you kind of use your own creativity, your own solution to, right? So you don't necessarily have to combine this test program with your test bench. Your test bench can use whatever testing methodology it wants. But when we demo your lab, one of the things we may ask is for you to run this test bench or this test program and watch the registers populate in QuestaSim. That's not the greatest way to test it, obviously, because there's no way to automate that, right? Like you can run this in QuestaSim and look at the waveform, but that's not automatable. That relies on a human being looking at the screen, right? So your test bench should have some automated way to test your CPU. Okay, so those are two separate things. And then the binary to decimal conversion is something else we'll want you to demo. And this is just a practical thing that we want to test. It's not necessarily for testing your CPU as it is, just having something demoable on the FPGA board. Does it make sense? So you want to put the switches up and have it convert the switch values to decimal. And so I mentioned in lab how to do that. And so the idea is to have the value that you want to have a value that you want to repeatedly divide by 10. The value comes in from the switches and you're going to keep dividing it by 10. So to do that, you multiply it by 0.1 in fixed point. So you'll have a 32-bit register with the value you want to divide that will have 0 fractional bits, and then the 0.1 value, which has 32 fractional bits. Now you might say, well, how do we know it has 32 fractional bits? Where are you defining that? Where are you programming that? It's all in the mind of the programmer, right? It's all in how the product is being interpreted, right? So by having that second operand as 32 fractional bits, and you set it to 0.1, which you can get, it's basically a magic number. You type it in. It's going to be 2 to the 32nd power divided by 10. You put that magic number in there as a constant. You multiply it by the value you want to divide by 10, and you'll get a 64-bit result, which of course you have to access with the mul HU combined with the mul instruction as two separate instructions. But when you use mul HU on it, you're going to get the value after it was divided by 10. And if you use the mul to get the fractional part, you're going to get the fractional part of the quotient. So, for example, if you put 1, 2, 3, 4, 5, and then you multiply it by 429,496,730, which is 2 to the 32nd power divided by 10 and then rounded. You have to round it. It ends up having to be rounded up. If you round it down, you're going to get some wrong answers, we found. Right? Sometimes you'll get the incorrect result. So you have to make sure you round this up. So the last two digits should be 30, not 29. So you put that in as a magic number and you do the multiply. And I confirmed this using a calculator that it's kind of amazing. Or actually, no, not this one. Sorry, this is the divide by 10. I confirmed the other one. So this one, you'll get 1, 2, 3, 4 in the whole numbered bits of the product, and you'll get 2 to the 32nd power divided by 2, which is 0.5, in the lower bits, which is 2,147,483,648. Okay, so basically, you've got two parts. The first part you're using as the input to the next step of the algorithm, right, which progressively divides by 10. And the other one you're using to extract the value that you divided out, the least significant base 10 digit. So this number you then multiply by 10, right? And then in the upper part, you should get the modulo. So in other words, if you have 2,147,000,000 blah, 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 right? You multiply that by 10, then the upper parts of the bit will be, in this case, 5. And the low bits will be 0. Right? So basically you take 0.5, you multiply it by 10, and you get 5.0. Now the question is, do you always get 0 here in the lower bits? I don't know. In this case you do, actually. This actually works out perfectly. You get 5.0. I don't know if that's always the case though, because there's some rounding involved. So you may get some rounding error down here in the lower bits. But that's okay, because you just ignore that. You're going to just use the upper 32 bits. So after everything is said and done, you'll have 3 multiply instructions. When you take the input and multiply it by 0.1, you have to do a mul and a mul HU, because you need to recover all 64 bits. But then, to do the second part, which is to calculate the modulo, you just need a mul HU. So for each digit, you need 2 mul HUs and 1 mul, right? So there's 3 multiplies to extract each of the base 10 digits, and you'll want to do that 8 times. Well, at least 6 times, right? Because if you put all the switches up on your board, it's 262,000. Technically, there's only 6 digits. But for the next lab, we definitely want to have all 8 digits recovered, right? Okay, now one thing that also confused, I didn't mention this, but what are you doing with each of these digits that you're extracting? Like basically, this is the digit you're extracting, 5, right? That input value is just being used as an intermediate value, right? The important result here is that, the 5. That's what we wanted to get. We wanted to take that 5 out of 1, 2, 3, 4, 5. And then the next digit would be 4. But what do you do with those digits? What do you do with them? Where are you putting them as you extract them? Well, you have to put them all into one register. You have to create what's called a binary coded decimal, which is where you have a 32-bit value and you're logically dividing it into 8 4-bit values, which means every time you extract the value, you have to put it into its specific spot, right, in that 32-bit value, which at the end you'll use the CSRW instructions and print it essentially on the hex displays, right? Now the trick is that how do you get them in the right order? Because the first digit you extract is going to be the rightmost digit, right? Then the next digit is going to be the second to rightmost digit. So the way I do it is every time you extract the digit, you can always put it in the leftmost position, right? But then before you do that, you shift the value down 4 bits, right? So you shift 4 bits, you insert the digit. You shift 4 bits, you insert the next digit. You shift 4 bits, you insert the next digit. So every time you put a digit in, it'll start out on the left-hand side, but it'll work its way to the right, all right? So the first digit will work its way all the way to the right. The second digit will work its way down to the second to the rightmost position. The third digit will make it down to the third to the rightmost, right? So basically that way you can take the same code and copy and paste it 8 times. Does that make sense?
You can use hex code also, right? Like use the decimal values as hex code and just display that. Like you can have a 0 hex bind 16 digits and you just keep adding hex code to that. For the most significant and the next significant.
Oh yeah, you can add. Yeah, you can add. Right. The point though is you have to have it in the right spot. Though you have to position each digit in its corresponding position. Right. Yeah, and shift by 4. Yeah, that'll work. Yeah, so I usually use OR. I use the OR instruction you take the digit, you extract this guy. The first thing you do is you shift it 28 bits to the left. You get it all the way to the left side, and then you OR it in with the running value that you're building up, right? So you take the running value, you shift it 4 bits to the right first. Then you take this guy, shift it 28 bits to the left, and then you OR it in, right? Okay, that's just one way. You don't have to do it that way. I think that's the simplest way to do it. I think in the end it only requires like 5 or 6 instructions per digit. And since we don't have a branch instruction, you have to unroll the loop, meaning you have to copy and paste it 8 times because we don't have any other way to loop, right, other than just the top level loop that continuously keeps rerunning your program. Okay, so I have a few tips for you. I don't know, again, these are optional. So I mentioned QuestaSim is a little funny to work with. You might have noticed I did some demos in lecture and I got tripped up because it wants to optimize your design where you can't actually plot the signals, right, in the waveform window. So the easiest way to avoid that problem is if you just launch ModelSim, QuestaSim, and then you tell it to simulate your design. If you just say simulate by itself, it won't optimize out your signals. If you make the mistake I did, which was to say vsim space top, right, or simtop, right? So if you start ModelSim and you tell it where to start simulating right on the command line, then it optimizes everything out, and then you have to re-simulate it from within QuestaSim. If, on the other hand, you just start QuestaSim and then you just simulate it from in there, it's fine. That's the mistake. I don't know if you guys saw that. I did a demo. I got tripped up over that. Okay. But the other thing is that even if you open the simulator and you can see the signals and plot them, it only records signals that you're plotting by default. So like if you add a few signals and then you run it and you add some more signals and run it, you'll lose the data for the signals that weren't there originally when you started running it, right? So a way to get around that problem is if you put this command $WLF dump vars 0, TB, you can put this in your initial statement, your initial block in the test bench. Test bench? Test bench, yeah. And this will make ModelSim plot or internally record all the signals of your design, even if they're not actually in the the waveform window. That's just, it makes it a little, it makes it so you don't have to restart the simulation so many times as you're debugging. The problem with that is it does not include RAMs. So for example, if you want to see your registers or your instruction memory, you'll have to add that before you can see it in the waveform. Does that make sense? So this is just for signals, not for memories. In other words, it doesn't apply to two-dimensional arrays. I don't know why. It should, but it doesn't. I guess they figure this it's too expensive to plot all your RAMs or to record, to log all the RAMs as you run it. Another thing that I found that's helpful is System Verilog allows enumerated types. This is something that was new. They didn't have this in Verilog. But in System Verilog, you can say type def enum, and then in curly braces, the syntax is weird, I know. I never remember this. I always have to look this up. But it's type def enum, and then in curly braces, you can put a bunch of like words in there, right? Like, for example, the instruction mnemonics. Now, some of them are reserve words, like and, although I don't know why and is a reserve. I mean, usually and in Verilog is an ampersand, but for some reason, the word and is also a reserve word. So you can see I put a little underscore after and there for that reason. But anyway, I put a bunch of mnemonics in there. And in the case of CSRW, I actually broke it into two separate ones, CSRW hex and CSRW switch, right? But anyway, then you say instruction name. So you create a type called instruction name. And then you can declare a signal, actually in this case two signals, instruction in execute and instruction in write back. And then instruction in write back is this clocked form of instruction in EX, right, with an always at pause edge clock. And inside your control unit, you can set the instruction in execute. This way, when you simulate, I don't know if you can see it very well there, but in that waveform I'm showing on the slide there, you can see the instruction in EX, and you can actually see an English representation of what instruction is being executed. Now that signal looks like it should be non-synthesizable, but it is. You can synthesize this, it just optimizes it out, right? So this has no effect on your hardware at all. This is purely for debugging. Now the reason I say to add this is because in your control unit, you have this big complicated if then else. And one of the common errors that students have in this lab is that because of the complexity of the control unit, sometimes the control unit will misidentify an instruction, right? Because it makes sense because there's the opcode and the two function codes. It's easy to accidentally structure the if statement in a way where you get like a false positive, like it thinks it's one instruction when it's really another, right? And so it's really hard to debug that. It's hard to figure out what the control unit thinks this instruction is, right? Like you have an instruction and it's not putting out the control signals that you want it to put out, and it's because it's confused, right? And you want to know why it's confused. You want to know where it is in the what line in the control unit is being triggered, right? What if condition is being matched. So this is a good way to do that. Also, it allows you to track the progress of your software from the hardware simulation. So as the hardware simulation progresses, you can see a list of all the instructions in your software being put on a timeline, right? Being plotted. So I think it's useful, and it doesn't, it's a little bit of a pain to set up because you got to put all the mnemonics in there. You can also put one in for like unknown. Like if your control unit has no idea, sometimes because your control unit has like a catch-all, like a final else. Sometimes your control unit doesn't even know what the instruction is, so you can have an enumerated value there for unknown instruction, right, or invalid instruction. And in real processors, if that happens, it typically will generate an exception, right? If you have an encoding that's not valid, it'll trigger an exception. It goes into the operating system and it kills the process. You get a seg fault, right? Okay. All right, so that's pretty much it for lab 3. Then lab 4, I'm going to start talking about that now, even though it seems a little early, but I don't want to get behind the labs in the lecture. So let's talk a little bit about how you would implement branch instructions. You guys remember how branch instructions work from 212? Do you? A little bit. Yeah, so the branch instructions, they do some kind of test, right? And then they'll either fall, if the test is false, or evaluates the false, or if the test fails, they'll basically, effectively, they act like a no-op. They don't do anything. They have no effect at all. They just go, you just go to the next instruction after you execute the next instruction after the branch, which is the fall through, right? If the condition is true, then they will go somewhere else other than the next instruction, usually. The way that target is identified is through a PC relative offset. So pretty much what the branch basically says in the instruction encoding is if the branch is taken, you put a skip number in there. The skip number tells you how many instructions to skip, up or down, and it's signed, right? So if it's negative, it means go up. It means go to a lesser program counter value, a lesser address. If the offset is positive, then you go to you jump down relative to the program, the program address, right? Okay, so the one thing that's weird though is they changed something in RISC-V versus MIPS. So in I don't know if you guys looked at it this closely when you were studying the MIPS, but in MIPS, the branch offset in terms, the skip number was relative to the fall through instruction. In other words, the skip number was relative to the next instruction in the instruction memory after the branch, which meant that if your skip was 0, if you had a 0 skip, your offset was your offset was 0. If your offset was 0, then if the branch was taken, it would just go to the next instruction, which is where it would have went anyway if the branch failed, right? If the branch condition was false, right? So in other words, if you had a branch instruction with an offset of 0, then it wouldn't do anything. It would never do anything, right? Regardless of the branch outcome, it would always just go to the next instruction, right? However, if you set the skip to -1, then you had a problem, because if the branch was taken and your offset was -1, it would branch to itself. And because you were branching to the same instruction, there was no opportunity for the branch condition to ever become false. It would just forever be true. So that would guarantee an infinite loop. There was no way to get out of that. You were finished, right? You basically would brick your computer if that happened, right? At least assuming you didn't have an operating system that could intervene and kill the process, right? So that was a -1, and by the way, I'm saying 1 deliberately because the branch offset is not byte addressed, it's word addressed, meaning that, well, at least in MIPS it was. It's not true in RISC-V either. But in MIPS, the skip amount was in the units of instructions. So a 0 meant no instruction skip, a -1 meant go back 1, but go back 1 relative to the next instruction, which means go to myself, right? However, in RISC, they changed that. Now, by the way, you can see this, by the way, here. This is in, check this out. This is Mars and RARS. The top is RARS, the bottom is Mars. So in RARS, if I have an instruction that says foo, branch to foo, and then you look at the corresponding offset, the offset is 0, meaning branch to myself. But in Mars, the offset was -1. Right? So what that means is that the branch offsets in RISC-V are relative to the branch instruction itself, whereas the branch offsets in Mars were relative to the instruction after the branch, right? So there was a difference of 1. Does that make sense? Okay, that's important for us because we have to calculate the offset in our hardware. And what are we calculating it relative to? Well, the only thing that I've showed you so far is PC fetch, right? PC fetch is the program counter in the fetch stage. That refers to the address of the instruction being fetched, which is the instruction that comes after the instruction being executed, right? So if I'm executing a branch and I look at PC fetch, then I'm using the MARS technique, the MIPS technique, right? In other words, my fetch is going to be, my PC is the address of the next instruction after the branch because of the pipeline, right? Because remember, I'm fetching the fall through while I'm executing the branch, right? So that's a big problem, right? How do we deal with that? Well, one way to deal with it is you can add a decrementer, right? You can decrement when you calculate the offset. You can subtract 1 from PC fetch. That's one option. That should work. I never tried it that way. That'll work. Another way to do it is to add a register, a pipeline register for PC. So then you can have PC fetch, but delayed 1 cycle is PCEX, right? So you can introduce a new signal called PCEX. PCEX and PC fetch are the same signal. The only difference is that PCEX is delayed by 1 cycle. It's a delayed version of PC fetch. But also, it helps for your debugging because PCEX is the address of the instruction being executed, right? Whereas PC fetch is the instruction being fetched. So it's actually, I think it's helpful to see that in your waveform because you know where you are in the code in terms of the execute stage, right? Not in terms of the fetch stage. Because the fetch stage is not very helpful because you don't know what's being fetched. You don't even have the instruction when you're fetching it. It doesn't exist in your CPU yet. Okay, so that's real simple, right? You just add always at pause edge clock PCEX equals PC fetch. Yes? Well, normally, yeah, normally you're incrementing as you march through the code, right? As you run through the code. But what I was saying was, for the purpose of calculating the branch offset, because when you're executing a branch, all you have to work with is the program counter and the offset. And from that, you have to calculate where you want to go if the branch is taken. So one way to do it is, instead of just adding them, because you don't want to add them because that would be invalid that's valid for MIPS, but not valid for RISC-V. So you could add them and then subtract 1. That's an option. Or you could subtract 1 from the program counter fetch and add the offset. Right? Right? Yeah, I think that works, right? Oh, you mean add 1 for the correction? Yeah, actually, you might be right. Yeah, sorry. You want to add 1 because the, well, no, because you look at PC fetch, that's fetching the instruction after the branch, right? Which means it would have been advanced by 1, right? So when the address of the branch would have been 1 less than that, right? So I think you want to subtract, right?
Because if it's -1, we want to make it 0, right?
Right. So if the 0, so let's say you have 0 as your offset. In RISC-V, 0 means infinite loop, right? So the 0 would mean that the target should be PC fetch -1, right? So I think that would work out. Yeah, the offset of 0 be PC fetch -1, right? Yeah. Otherwise, if you use PC and your offset is 0, then you're just going to go to the next instruction. So I think that's right. I've never done it that way before, though. It requires, see, the problem with that is it's cheaper to just delay PC fetch than it is to incorporate another subtractor, right? Because it's the 32-bit subtractor, so... Well, no, it could be, well, in our case, it would just be a 12-bit subtractor. So it wouldn't be too bad. But the difference, it's a trade-off. You either delay it or subtract 1.
A common practice is to have these games, or like how in general RISC-V handles it?
That's a good question. I don't really, I've never seen how anyone else does it. This is something that we've come up with in this class. But that's a good question. I'm not sure. If you were to download a reference design from some Berkeley or GitHub or something, then it would be interesting to see how they do it. Yep. My guess was they probably would delay it. I think that's more, because it's pretty common to have your pipeline registers in there. Actually, in their design, it would actually be a little bit of an exacerbated problem because they would have a decode stage in between fetch and execute. So by the time the branch gets to execute, now the PC's been incremented twice. Because there would be a 2-cycle lag before the branch gets, so they would have a little bit more of an issue. And then, of course, if you have a more deeply pipeline processor, there would even be more of a lag. So, yeah, and that lag is really the problem with branches. There's other issues. There's more serious issues when it comes to that that I'm about to get into. Okay, so, but one of the other problems, and this is ridiculous, I don't know how they came up with this, but so you would think the offset for the branch would just be in the immediate field, right? For the I-type instruction, right? Because you guys might remember, in MIPS, the branch instructions are I-type instructions, and they had a 16-bit immediate. We also have I-type instructions, but they don't use them. They use the B-type instruction. So this is a new encoding format. The reason they do that is because with a branch instruction, you don't need a destination register field, the RD field. That's 5 extra bits we can use, right? And also, the I-type instruction only has a 12-bit immediate, which doesn't give you much range for branching. So they introduced this B-type format where they take the immediate field and they combine it with the RD field. I believe that's where the RD field normally sits, right there, right? The RD field. And they combine them. They combine the 12 bits with 5 bits, so they get like a 17-bit effective offset. But the bits are all scrambled. So, and this is weird. I cannot explain this. So they have bit 12. Okay, so this is always so hard to explain. So the immediate field is actually 13 bits. I think I did the math wrong there, right? It's 13 bits, but it doesn't include bit 0, so it's actually 14 bits. 14 bits. I don't know. Wait, yeah. So the immediate field is called IMM, and this figure is taken directly from the RISC-V ISA. Okay, so what this means is that if you look at the bits in the upper part of the instruction, you've got the immediate bit 12 concatenated with bits 10 down to 5. And then down here in this field, you've got bits 4 down to 1 concatenated with bit 11, which is weird. So here's how I rationalize this. I created 2 tables to decode this. So in this table on the left, this is mapping the instruction bits to the offset bits. So bit 31 is offset bit 12. You can see that here, right? The first bit is 12. Then bits 31 down to 25 from the instruction match up to offset bits 10 down to 5, which again you can see here. And then bits 11 down to 8, this is 11 down to 8, which you can only get by sort of counting because they don't have the original instruction bit indices here. So 11 down to 8, which is this field down here, maps to immediate 4 down to 1, and then bit 7 matches bit 11. And obviously the opcode is 6 down to 0, right? Because there's a 7-bit opcode, right? Okay, so but then to make any sense of this, you have to invert this table, because what I really want to know is I want to know how the offset bits map to the instruction bits. I don't really care how the instruction bits map to the offset bits. So I took this table and I effectively inverted it. So what that means is that the offset now is defined in terms of bits 12 down to 1. Now, first of all, you might say, where's bit 0? Well, I'll get to that in a minute. We've got bits 12 down to 1 of the offset. So bit 12 of the offset is instruction bit 31. Then you go to a bit 11 of the offset is instruction bit 7. Bits 10 down to 5 of the offset bits map up to instruction bits 30 down to 25. And finally, 4 down to 1 map to 11 down to 8. Okay? Which means that you can recreate the offset pretty easily with this line of Verilog, which I just give you. Assign branch offset and then use the curly braces and just put all these bits together, right? Now you'll notice that there's no offset bit 0 here. Just like you can't see a bit 0, there's no immediate bit 0. That's because it's assumed that bit 0 is 0, right? So you can see I concatenated a constant 0. What that also means, now if you remember from MIPS, MIPS actually had 2 zeros they added to it, right? Because it was a skip in terms of instructions, 32-bit values. It wasn't a byte address, it was a word address. So they added, effectively in MIPS, they were adding 2 zeros. And here they're adding 1 0 because this offset is a 16-bit addressable value. Why do they do, like nothing is 16 bits. Why do they use 16 bits? I don't understand. Well, because there's a version of the RISC instruction set that's a 16-bit version. That's why. RISC has a 16-bit mode for very highly constrained hardware. Like if you have a really power limited CPU where you don't have a lot of memory, you can actually have a 16-bit version of RISC. That's why they did that. So this branch offset is in terms of 16-bit words, not 32-bit words. ARM has that too. It's called ARM thumb, but they try to reproduce that with RISC. Does that make sense? Okay, but our instruction memory is actually word addressed. So we are actually end up taking that extra bit off. We're going to knock that bit back off, and we're also going to delete the next bit over. Okay, so if you look at the next line of code, I have the branch offset, which is calculated in terms of the RISC-V spec. But then, when I add the branch offset to the program counter EX, we actually end up only taking it down to bit 2, which means so what that means is the branch offset is byte addressed because it was a 16-bit, we added a 0, we made it byte addressed. I mean, it was 16-bit address, we made it byte addressed. But then down here in this line of code, we made it word addressed again by deleting the lower 2 bits, right? So that's what's, now I know that's confusing, that's why I just gave you the code for this. You can just copy and paste this. But I wanted to explain what's going on there. Now you might say, well, wait a minute, why is there an extra 12? Bit 12 is duplicated here. We got bit 12 here and bit 12 here. That's because the branch offset ends up being 11 bits, I believe. And the program counter is 12 bits. So I basically just sign extended the offset. Make sense? Okay, so you can just use that code. So the branch offset is basically, in terms of byte addresses, what the offset of the branch instruction is, if it's a branch instruction. Otherwise, it's just garbage, so don't care. And the branch address is where you actually want to go in your word addressed memory for that branch. And this assumes that we have a PCEX, not a PC, that we're not using PC fetch. Okay? All right. Okay. Any questions about that? Okay, so those are branch instructions. How many branch instructions do we have? Fast forward here a little bit. Here we go. So there are, so RISC-V has 6 branch instructions. Branch of equal, branch of not equal, branch less than unsigned, branch greater than or equal, branch greater than or equal unsigned. So there's only 6 possible ways to compare 2 numbers, and we have hardware instructions for all 6. You guys might remember from 212 that in MIPS, some of these instructions were pseudo instructions because MIPS emphasized the branch of equal to 0, branch of greater than 0. So MIPS had this, compare one register to 0 business. RISC-V is all branch instructions compare 2 registers, and if you want one of them to be 0, then you just use register 0. Right? And these are all hardware instructions. None of these are pseudo instructions, so you have to implement all 6 of these. Okay? In the next lab, not in this lab. Okay. Does that all make sense? I know that's confusing, but the bottom line is that RISC makes it very difficult to figure out what the branch offset is because they scramble the bits in the instruction encoding. And again, that's called a B-type instruction where they do that. B for branch. In MIPS, they wanted to have just like minimal number of encoding formats, where in RISC-V, they threw all that away. RISC-V has lots and lots of instruction encodings. That wasn't their priority to minimize those. So B-type is kind of like I-type, but not the same. Okay, well, how about jump instructions? So those are different. Jump instructions are unconditional. They don't have a condition, but jump instructions, unlike MIPS, always write a return address to the register file. So, and of course, if you don't want to do that, you just say X register 0 as your destination. Okay, so all jump instructions write the PC fetch. Well, I should be more specific. All jump instructions write the address of the instruction after the jump to the program, to the register file, sorry. So you can get back to where, so you can return, right? You guys with me on that? Like, so this is meant to implement methods, so you can call a method and return from the method, right? So jump instructions write a register. Branches don't. But jump instructions have an even more strange addressing format. So they use J-type. So this is yet another instruction encoding format. This one has an opcode, an RD field, and then it has the rest of the bits are the immediate. But they're out of order. They're all scrambled. So they have immediate bit 20 concatenated with bit 10 down to 1, concatenated with bit 11, concatenated with 19 down to 12. I have no idea why they do that. So at some point, we'll figure this out. I don't know why they chose this ordering, but these bits are all out of order. But that's okay, because we've figured out how to interpret this, and so we've given you the lines of code here. So we have two assigned statements, JAL offset. This is for the jump and link. JAL offset and JAL address. JAL offset is the byte address of the offset because it's consistent with how it's in the RISC spec. And the JAL address is meant to be the program counter value that you want to jump to, right? So one of them is an offset and one of them an address, because the address obviously incorporates the program counter in there too, right? So you got the offset, then you add it to the program counter and you get the target. And so we give you two lines of code. Again, you don't have to use those, but we just try to make it a little easier. Now, the register, so I did the same thing, by the way. I have a table that maps the instruction bits to the offset bits, and then the offset bits to the instruction bits. So these two tables are just inverted forms of each other, and they're meant to help you understand how the bits and the instruction are used for the offset. Now, the register destination, though, is used to write. Now, this is a little misleading. So, fetch, PC fetch, but this is assuming that we're writing this when the jump instruction is in the execute stage. Okay, so the idea is that the value that you're writing to the register file is the program counter value associated with the instruction immediately following the jump, which is the PC fetch when the jump's in execute. But of course, when the jump is in the write back stage, then it's the PC EX, right? So be careful with the timing, right? You want to make sure that whatever you write back to the register file is the program counter that comes, the address of the instruction that comes after the jump, which is the one stage earlier in the pipeline, right? Now, what does that mean, though, for us? What are the implications of that? Well, remember that mux that we had that goes to the register file? This mux here, reg select this mux. This mux only had 3 inputs, right? But now we have to add a 4th input to it for the program counter. Is it fetch or EX? Well, it'll actually be EX, because it is fetch, but it's the delayed fetch, right? So basically, very simple. It's actually not too hard. You just add a 4th option, and you don't even have to change the width of reg select, because it still can be 2 bits. You guys with me? So that's a pretty easy modification to our pipeline to support writing the program counter. Of course, you have to draw a wire from the, well, not draw, what you have to, have the program counter be an option for that mux. Okay, now there's also a jump register instruction, which is also writes back like the jump and link, writes the link address, the return address, the fall through address. But the jump register uses a different way to address. It takes the contents of a register and it adds that to the program counter instead of having just an absolute, like an immediate, right? This is not, I should, hold on, I have to correct myself. It also uses immediate too, though, but a smaller immediate. So check this out. It takes the contents of the RS register, adds it to the immediate, but it's just a 12-bit immediate, so it's a tiny immediate. And then it adds it to, and then it uses that as the offset. So the jump and link instruction in RISC-V allows you to have both an offset that's in a register, which is a dynamic value, as well as a constant that's in the instruction, in the immediate. But again, we're going to give you that code here. So here's the code that'll do it. Jump and link register address equals read data 1 EX, that's the value coming out of the register file. Of course, only the lower 12 bits of it, because we don't need all 32 bits, because our program counter is not 32 bits, at least not in this class. And then we add the Jaller offset, and the Jaller offset comes from the instruction. In this case, just 11 bits. 12 bits, 12-bit immediate, sorry. 11 down to 0. Well, actually 31 down to 20, technically. Make sense? Okay, so again, a little confusing with the addressing, but we'll give you that to make that a little easier. Okay, so what you end up with here is, okay, so here's what your fetch stage will end up looking like. So your program counter previously just blindly incremented each cycle. But now we have to provide, in addition to the PC plus 1 as an option for the next program counter value, we have to add the branch address, the JAL address, and the Jaller address. Now, keep in mind that those three addresses are garbage in the cases where the instruction is not that instruction, right? So like if you have an instruction that's not a branch and not a jump, then those values are, not legit, right? Because they're calculating values that don't make any sense because they're not jump or branch instructions. But that's fine because they won't be selected anyway, right? They're don't cares, right? You see what I mean? So these values are calculated for all instructions, even if they're not branch or jump instructions. But if they are, then we will be able to pick the appropriate target address, and it's selected from an additional control signal that you guys will add called PC source. PC source is where to get the next PC value, right? And that'll come from the control unit. Now, obviously, it depends on whether if it's a branch, the PC source will depend not only on it being a branch instruction, but if it's a taken branch instruction, right? But a jump, they're unconditional. So if you get a jump instruction, then it'll just set the PC source based on the instruction. Okay? Does that make sense? Okay, now you'll notice I have this stall thing in here, which we'll have to talk about next week. So there's another important implication of jumps, which is when the jump instruction or the branch instruction gets into the execute stage, right, we're already fetching the fall through instruction. And by the time the jump or branch instruction completes execution, then we will have already completed fetching the fall through, and meaning it's too late. It's too late. You've already got the fall through instruction before you even know it's a branch or whether it's taken or not, right? So as a result of that, if you have a jump or if you have a taken branch, you're going to have to kill that next instruction that has already been fetched. You have to stall it. You have to convert it into a no-op. As it passes from the fetch stage to the execute stage, it has to be converted into what's sometimes called a bubble or a stall or a no-op. You have to kill that next instruction because of the nature of the pipeline, it's already too late to do anything about the fact that you've already fetched the fall through instruction, right? The next instruction, which means that the number of instructions your pipeline processor will execute will now dip below 1 per cycle, because you're going to end up with, every time you have a branch or a jump, you're going to end up with cycles that effectively don't do any work, the stalls, right? So you're going to go below 1 instruction per cycle here. But dealing with those stalls is tricky with the control. And so I'm out of time for this lecture, but we'll talk about that next time.